Electric charge is discrete. Only point charges exist in nature, and the smallest possible charge is the charge of an electron. However, in this course we will often use a concept of charge density to describe continuous charge distributions. Continuous charge distribution is an approximation. It is only valid when we are dealing with many millions or billions or even larger numbers of small point charges. Then we can think of them as a continuous charged fluid. Those charges can be located along a line or wire, on a surface or inside a volume. Depending on the geometry, we would talk about linear charge density, surface charge density and volume charge density. Charge density is simply the amount of charge per unit length, per unit area or per unit volume. They are usually denoted by Greek letters lambda, sigma and rho. They are measured in coulomb per meter squared and coulomb per meter cubed. Moving charges result in currents. A current is a total amount of charge crossing a given surface per unit time. A current density is the current per unit of surface. Both the current and current density are vectors. They point in the direction of moving charges. Once the charge density of an object in question is known, we can use integration to work out the total charge of that object. We just use an appropriate charge density and integrate it over the relevant geometry, be it a volume, a surface or a line. Consider a volume V, bounded by a surface S. If the charge in the volume is neither created nor destroyed, the current I of t leaving the volume can be expressed in terms of the current density as an integral of the current density over the surface. As current is defined as the rate of change of charge with time, this rate of change of the charge inside the volume must then be equal to the current flowing out. The total charge in the volume is defined as integral of charge density over the volume. Then the current is given by the integral of time derivative of charge density over the volume. We can now combine the two equations and get, remembering the divergence theorem, we can replace the surface integral of the current density by the volume integral of its divergence. Then we can drop the integral sign to arrive at the differential form of the continuity equation. The continuity equation is nothing else but the expression of conservation of charge. As far as we know, charge is always conserved in nature. It neither appears or disappears. Charged particles can, of course, appear and disappear, but they always do it in pairs of opposite charge. So the total charge does not change.